Hello, everyone. Welcome back to the course of probability and statistics. We finished talking about introductory probability, so to speak. Today, we are going to go into more advanced stuff. So we will discuss um, when probability, there are models of probability. You will see that there are specific events in life that we can model through probability using specific functions. So before delving into that, let's start with talking about the types of random variables that we are going to deal with. A random variable is a representative of a particular distribution. It's basically a function, like any function you learn in math. So there are two types really. Like you have two types of not two types of functions, but I mean two general types of function. You remember when you started uh, learning about functions and you were told that when I say y equals a function of x, I can give you that in form of a table where I say, well, when x is 1, y is 3, and when x is 4, y is 7, whatever. Or I can give you a function like y equals x cubed minus 4. Okay. So one of them is only at specific points. So I tell you this, when you graph it, you get a point here, a point there, a point there. But the second type is continuous, that is connected line. Okay. Similarly, in probability, we have events that can be modeled as just specific points, or sometimes we make them lines so you can see how it's shown or how we can represent it. Um, and we call these discrete random variables. It's basically a function of specific points in X versus specific points in Y, but there is nothing in between. Like counting. I cannot say I'm going to, throw a die 10 times. What is the probability of getting exactly 3.5 heads? Doesn't make any sense, right? So that's why it's only defined at specific point. Normally it's counting, but sometimes it's not, but generally speaking. So we call these discrete random variables. Today we are going to talk about general random variables. Like I'm just out of my head, I'm giving you points between values between x and y, or x and f of x. Okay. And next time, probably if we finish that now, next time we'll talk about um, the specific models I was talking about that deal with real life situations where you will use a specific function. Okay. So like I can remember when you will be given like a part looking like that and a straight line, and then we were talking about, say, continuity or differentiability and stuff. So we are making some equations that have nothing to do with each other, and we tell you to deal with those. And then we came and told you, oh, let's see. Now, if we have a polynomial function, that's how we deal with it. If we have a rational function, that's how we deal with it, and so on and so forth. So we'll be doing something similar. We'll give you just general things so you can see how it works, and then we'll tell you, oh, by the way, this event in life, we can model it using this particular distribution or function, and this by that function, and so on and so forth. So just to give you a quick idea. So a discrete random variable, as we said, is a function that gives me for every, not every, but for specific values of x, a corresponding value of y. So to give an example, let's say I have a random variable. I'm not going to tell you what that is. I just made it up. Okay. Where x, my random variable, and instead of saying y, we usually say in math, we say f of x, right? Here, sometimes you will see the term p of x, and p stands for probability. Anyway, and we say x can take three values, 2, 5, 7. And I'm not going to give them equally spaced, so you don't get the idea that I have to add 3. No, they can be any three numbers. Think about it as probably I might have mentioned that before. I have a big urn, and then inside it, I would place three different types of balls. Some have the number two written on them, some have the number five, some number have the number seven, or there, whatever. That's a code for colors, whatever the case. And let's say I'm going to place 100 balls. Okay, I want you to think in terms of probability now. 30%, so I'm going to write it 0.3, 30% were red, 25% were green, and 45% were blue. Okay, meaning I have 30, 25, and 45 balls. And then you are going to turn them around, close your eyes, pick one at random. What is the likelihood that you get a 2? 30%, a 5, 25%, a 7, 45%. We call that a probability mass function. Okay? Probability mass function, meaning there are masses only at this point, and that point, but it's void in between. You will see in a second, and maybe two sessions later, why that makes sense. Okay. And if you want to plot it, that's so easy. I mean, here is the x, here is the PMF or P of x at 2, at 5, at 7. You get a line of height 0.3, a line of height 0.25, and a line of height 0.45. So what do we notice about these probabilities? Number one, that P of x has to be greater than or equal to 0. There is no such thing as negative probability. Because the worst case is that you won't get the number that you want, and that would be 0, right? So you can think of it is that if I pick 10 times, on average, that's not guaranteed. On average, I will get 3 red balls, and 7 times I will get a different color. Here, 25 times if I run it, of course, 10 times you cannot get 2.5. So we can say 20 times you will get one of them to be green, and the rest would be non-green. And here, if I run it also like what? 45. So you can say, even you can say 45 times, right? 45 times. No, I'm sorry, not 45 times. If you get 40 times, you get 18 of them would be blue, and the rest will be non-blue. But that's the idea, okay? So we say the probability cannot be 0, and then the summation of all p for all I of the probability of x sub I add up to 1, exactly 1. I can't have a probability more than 1. You might have heard some people, especially back in my country. I haven't heard it here a lot, but sometimes that people would say, "Oh, oh, that's a guaranteed. That's a sure event. It's guaranteed. It's 100,000 times or 1,000 times. So the probability of it is 200%, and there's no such thing as 200%. If you are sure, it's 100%, whether you are really sure or extremely sure or, oh my God, I swear it's sure, it's still 100%. So don't try to emphasize it using your own words. Okay, so that's PMF, very simple. We are simply drawing. Remember, in math, you would place a point here, and a point there, and you say, okay, that's a probability because, for every x, there is only a unique value of P of x, and so on and so on. But we say specifically, I cannot go below. There is no negative. And when I add these numbers, I should get 1. Okay. Next, we look at what we call the cumulative distribution function, or sometimes just the distribution function. A distribution function gives you, so capital F of x. So if you do the small f of x, usually we use that capital F of x, and you say, but we are using P of x. I said most people in probability use P of x for probability mass function, but if you write F of x, it's still correct. Okay, but capital F of x means the summation from I going from negative infinity up to x of f of I, f sub I of x, or f of x sub I if you want. Yeah, so f sub I of x. So it's like you are coming from negative infinity and see. So if I say, for example, what is f of 4? Here is the number 4, right? If I say p of 4, it's 0. But if I say f of 4, it means I'm coming from negative infinity on this graph, and I found something at 2. And since 2 is less than 5, less than 4, I say it's 0.3. And then I keep going. I reach 4 here. There is nothing else. So it's 0.3. If I say f of 6, then I get 0.3. 5 is less than that, so plus 0.25 equals 0.55, which is incidentally the same as f of 5, because we said f of x is the summation for all, you can say less than or equal to x. So if I want f of 5, I get f of 2 plus f of 5. So anyway, I get the same result. So if you want to do it in a table form, 2, 3, oh, I'm sorry, 2, 5, 7, then f of x would be 0.3, 0.55, and definitely 1.0. When you reach the last number, you have to be at 1.0. And if you try to draw it, if this is f of x, and this is x, then 2, 5, 7. We call that in math, or even in engineering, this is an impulse. Okay, you get a pulse at 2 and nothing, and then a pulse at 5, nothing, a pulse at 7, nothing. So we say that the integration of that, notice we say f of x is the summation of lowercase of f of x. So when this becomes continuous, the summation becomes integral, right? And the integral of this impulse is a step function. You must have learned that, or if you took calculus or differential equations or Laplace transforms, you have seen that. If you haven't, you will see it, don't worry. So you get 0.3, and then it keeps a step. And when it reaches 5, it jumps again 0.25, so it reaches 0.55. It stays like that until 7, and then it jumps to 1.0. I don't stop here because it stays at 1.0 till infinity. So if I'm taking the cumulative of any number less than 2, it's 0. So anything from negative infinity up to 2 minus, the limit as 2 approaches 2 from the left, it's 0. If I am between 2 inclusively and 5 exclusively, meaning if I'm approaching 5 from the left and getting very close, it's 0.3. Once I hit 5, it jumps and it stays 5 until 6.999999. And then when I hit the 7, it stays 7. So f of 100 is 1. F of a billion is 1. Anything higher than 7, f of 7.1 is 1. Okay, so anything higher than 7 becomes 1. Okay, so these are the two functions, the probability mass function and its summation, or the cumulative distribution function. If I want P of 5, for example, I can say it's f of 5 minus f of 2, or f of any number less than between 2 and 5. f of 3, for example. It's okay. But usually we look at where the function is defined, right? We say, if I want the probability of 5 by itself, I take this big thing, which is f of 5, but then I subtract what's before it. Before it was 2, which is 0.3, so I get 0.25. Of course, it is 0.25. But if I didn't have that and I had this, I can find the probability of a particular event. Okay, so that we are done with these functions. Now I'm going to take the same example and tell you, because we need to define other stuff. So here we had x, p of x. They were 2, 5, 7. We said 0.3, 0.25, 0.45, right? Now if I ask you, what is the mean of x? First of all, what does it mean? I'm not trying to be mean, but what is the mean of x? Which is basically when we say the average in statistics. We call it the mean of x, or E of x, where E here stands for the expected value of x. The expected value of x most of the time, 99% or 99.9% of the time, will never be 2, exactly 2, or exactly 5, or exactly 7. I can make it equal, but it may not. And you say, what? We learn in school that if I have 3 numbers and I want their average, if you say the mean or the average, I add them and divide by 3 if they are 3 numbers. So I get 14/3. I say no, because you were taught it incorrectly. If you are teaching probability, always think of uncertainty, of something you don't know the outcome of. So it's impossible to know ahead of time that the average would be something. You say, no, but that's how we learn it. I say, yes, because the way you should have learned it is as follows. We assume we have an urn that has balls. I can have 3 balls or multiple of 3s. I can have 9, I can have whatever, okay? But number divisible by 3 for that. Some of them have the number 2 written on them, and some have 5s, and some has 7. So let's make that 5, another 7, another 7. We are going to shuffle them, and I say, what is the probability, or what is the average of them? Suppose, what is the likelihood that I get a 2? So for 2, for 5, for 7. If there are 3 out of 9, so the likelihood I will get them is 1/3, right? The probability of getting 3 out of 9. Same thing for this guy, same thing for that guy. Oh, not same thing, okay? Or you can think about it somewhat differently. We will see why you were taught this way. I am telling you the way to find this mean is to multiply 2 times 1/3 plus 5 times 1/3 plus 7 times 1/3. So it's 1/3 times 2 plus 5 plus 7. Oh, I added all 3 numbers and divided them by 3. No, just an example, just a specific case where the numbers are equal. Because I could have said, well, the way you would learn if you had 9 balls is to say 2 times 3 because 3 of them, plus 5 times 3 because there are 3 of them, plus 7 times 3 because there are 3 of them, and then you divide by the total number of 9. So 3, if you factor out 3, you get 3 times 2 plus 5 plus 7 over 9. You get 2 plus 5 plus 7 over 3. But that's only if the numbers are equal. Here, as I told you earlier, I can think of that as having 60 balls, okay? Or any number that is divisible, so 100 is easier, of course. 30 were red, we said, 25 were green, and 47 45 were blue. And then if you add them up, you would say 2 times 30 plus 5 times 25 plus 7 times 45 divided by their total, which is 100. Notice that 30 over 100 is 0.3, 25 over 100 is 0.25, and 45 over 100 is 0.45. So the way we do calculate the mean, I wanted to clarify that because I've seen over the years a lot of problems. We spend time explaining the mean and the expected value, and in the test, they ignore the probabilities and they say 2 plus 5 plus 7 over 3. I would be so frustrated. And then I thought, okay, maybe where is the root of the problem? The root of the problem is when you first learn probability and think that it's just you are looking at the numbers without understanding the meaning. No, it's not the sum of the numbers. It's the likelihood of selecting a 2, and you multiply 2 times that likelihood, which in this case is 1/3, plus 5 times the probability that you would select a 5, which is 1/3, plus 7. And why don't we divide by anything? Because the sum of the probabilities is 1. The total sum is 1. Remember when we said all the probabilities are conditional, but we don't write it as a conditional because you say the probability of an event and the sample space is the probability of the event. And if I divide by the probability of the sample space, it's 1. So we don't write it. Same thing here. We don't divide by anything because the sum is 1. I could have divided by 1. I could have said 2 times 1/3 like we did here. Or in this case, in our case, we say 2 times 0.3 plus 5 times 0.25 plus 7 times 0.45 divided by 0.3 plus 0.25 plus 0.45, which is 1. But I could have done it like 30, 25, 45 and divide by 100. I will get the same result. So that is the mean. That is the correct way to calculate the mean. Okay? And even remember when you had a problem that tells you have, um, well, I don't want to spend more time. I think you got the point. So I get here 0.6 plus 1 1/4 plus 3/15-ish. So you get, wow, we get exactly 5. I'm getting out of here. Oh my God. I wanted to give you something that will not. Okay. It's a middle point. I told you in the beginning, 99% of the time you will not get exactly 2 or exactly 5 or exactly 7, but then here it's this exception. It's always like that with me. It's like all my life is full of events that are incredible. It will never happen. It's not, the time to tell you one of those, but just to give you a hint, and believe me, I swear, I don't have a proof for it. It's only my word, and I know you don't believe me. But anyway, assume I'm telling you the truth. Muhammad Ali, the famous Muhammad Ali, helped my wife when she was a kid back in Egypt when he came to visit us. And she had her picture on the front of an Egyptian magazine. Roughly 30 years later in Kentucky, which is the birthplace in Louisville, the birthplace of Muhammad Ali, the late Muhammad Ali, the great. He had the Parkinson, so I cannot claim that but he hugged my daughter when we met by chance in a parking lot. And I got the goosebumps. And I told him, sir, well, first of all, it's an honor to see you and shake hand with you. But I'm going to tell you a story that you won't believe. And even if someone tells to me, I wouldn't believe him. You did the same thing to her mother almost 30 years ago in Cairo. So talking about rare events that happened to me, it's out of this mind. It's incredible. Anyway, going back to our nice stuff of probability here. This is the mean, okay? And of course, it just change the numbers and you will get a number that has nothing. So if I made that 0.2 and 0.4 and 0.5, you'll get 0.6 plus 1 plus 3.5, and that's 5.1. Not a number, not a possible outcome, right? So the mean doesn't have to be a possible outcome. But how can I explain it better? I would tell you, if you were following the statics course and looked at centroids and looked how you calculate centroids, you would say, this guy is crazy. What does that have to do with statics? It does. Suppose I have a bar, and this bar is fixed at 0. It's fixed here at 0. And then I put a weight of, say, instead of saying 0.3, let's say I have 30 pounds placed at 2. 25 pounds at 5, and 45 pounds at 7. And I say, okay, where is the center of mass? Meaning, if that was a seesaw, that's one way to think about where should I place the lever so that this bar stays horizontal. Or another way to think of it, if you already took a course in statics, I would say the moment produced by these three forces, I want to replace them by a single force called the resultant that produces the same moment. It's the same thing. So if I take the moment of these, I would say 2 times 30, 2 times the perpendicular distance from O, plus 5 times, I'm sorry, yeah, the weight times the perpendicular distance, in this case, it's 5, plus 7, the distance times the weight. And of course, I will get 60 plus 125, which is 180, plus 315, which is 500. Now, I'm going to replace that with the resultant. The resultant is the sum of the forces, which is 100. So where should I place 100 so that when I multiply it by the distance, I get 500? Of course, at 5. A weight of 100 at 5 would give me the same exact result as that. And that's where I should place the fulcrum, by the way. Okay? If you get a 5, you get 315, yeah, 440, and 60 is 500. And you can see if the fulcrum is here, and you have a weight of 30 at 2, meaning the distance is 3, so it's trying to rotate in this direction. 30 times 3 is 90. And here you have 45 at a distance of 2, so it's trying to rotate. 45 times 2 is also 90. They cancel each other, so the bar stays horizontal. So that's a combination between probability, which is something, never known to occur exactly, and statics. So you see, weird stuff. The last thing I want to go over, so we don't make it very long lecture, is we say this is a measure of location. Like, where is this thing is about? So it's around 5. When you look at the numbers, it's probably around 4, 5, something like that. Mathematically, we say it's exactly at 5 in this example. You were so lucky to get that. But then I want to look at a measure of variability, and we use the variance to represent that. The variance is a representation. Some people use the range, right? They say 7 minus 2 is 5, so that's how wide it's good, but it's not as good as the variance. The definition of the variance of x, but we usually use sigma square of x to represent the variance. Notice that we call the mean and the variance parameters of that particular distribution. And we usually, when we refer to a parameter, we use Greek letters. So here, instead of saying e of x, we call it mu of x. So this 5 is mu of x equals 5. Okay? Mu instead of m, Greek for mean. Sigma instead of S, And we'll see when we use S, when we use sigma. That's a topic for another day. And the definition of that is the summation for all possible values of I of x sub I minus mu of x, mu is a constant, quantity square times the probability of x sub I. What? Yes, it is the difference between x. So here I would say it's x, which is 2, minus 5, which is the mean, quantity squared times 0.3. Do you see that? I see how far it is from the mean, and then I multiply it by 0.3. How far it is from the mean, which is 0 times 0.25, plus how far it is from the mean times 0.45. So I get 9 times 0.3. Notice negative 3 squared is positive 9 plus 0 plus 2 square, so plus 4 times 0.45 equals 2.7 plus, notice that it never be minus. We always add, even if this number is negative. Variance cannot be negative. It's impossible, okay? 2.7 plus 1.8 equals 4.5. That's the variance. If we find the standard deviation, which you are more familiar with, of a function, meaning of a probability distribution, we call it sigma sub s, sub x, also sigma because it's a parameter. It's the positive square root of 4.5. Okay? So you can calculate that with a calculator if you want. So it's the square root of 4.5. It's roughly 2.12. I should have known. Anyway, now I'm telling you there is an easier formula, especially if the x's are integer like that. And that formula for v of x is the summation for all possible values of I of x sub I square times the probability of x sub I minus mu sub x square. So what does that mean? I'm going to notice I said if they are integer because it's easy to square 2, but not easy to square, say, 2.74, right? So this becomes 4 times 0.3 plus 25 times 0.55 plus 49 times 1 minus 25. What am I doing? I'm multiplying by the cumulative. I said that doesn't make any. How do I multiply by 1? This is 0.45. Okay, so let's try. The square of 2 is 4 times 0.3. The square of 5 is 25 times 0.25. The square of 7 is 49 times 0.45. And then I'm going to subtract the mean. The mean was 5, so I'm going to subtract 5 squared or 25. You get exactly 4.5. So instead of, especially if the mean wasn't 5. So suppose the mean was like the other example, 5.1. This would be negative 3.1 square, which is 9.61. And then this is zero point 0.1 square, 2.1 square. It's easier to square integers in your head. So you know the 9, the 0, the 4 right away. As I said, if the mean was, for example, 4.871. You have to say 2 minus that, and then you definitely need a calculator, right? Plus 5 minus that square, plus 7 minus that square. But if these numbers um, were integers, you can do this quite easily, and then at the end you subtract 4.871 square. So that's the only thing you would do. But the other math is the same. And then after that, of course, you take the square root to get the standard deviation. I will stop here. This is too much to cover. But next session, we will be looking at specific probability distributions that we use in real life or we encounter in real life. So we have a mathematical model for them. So instead of giving you X and its probability, you come up with these probabilities and you will see how easy that becomes. Thanks for your time and have a great day.